and this is good. Okay. Yeah, it is thrilling to be here. Thank you so much for your hospitality. It's been a joy to talk a little bit about AI yesterday. We had a nice casual session, and I'm always open if you want to shoot me any questions or chase me down while I'm here or send me an email later. Always happy to talk about AI in the form of large language models. But today I'm going to actually talk purely about science. And I think it's a really thrilling time to be an astronomer, to really work, especially in observational astronomy. I noticed that Yenting is wearing his LSST shirt, and that really commemorates the fact that yesterday was the first day of LSST, the survey, the legacy survey of space and time. And that's going to continue for the next 10 years. I also had the privilege of working on the Roman Space Telescope for 2 years as an instrument scientist, and that is set to fly and survey the wide field high latitude extragalactic sky, as well as the bulge and the Milky Way plane, and that's going to fly in about 2 months. So it's very exciting to be studying large data sets that our cosmos sends to us. But also, we know that this is an unprecedented time to be using data-driven methods. These two sort of innovations have risen in tandem, just being able to survey the wide area sky very efficiently, and to be able to use that data and turn it into science. So I think this is going to transform what astronomy looks like, and that's why I've titled this Astronomy Re-envisioned. I hope you'll help envision with me a future in which we're able to leverage targeted, detailed observations, new data, on the basis of what we can learn from large archival or survey data sets facilitated by machine learning methods. Okay, so over this next 45 minutes, I'd like to re-envision what astronomy can look like, and we're going to get started with a roadmap of what I'd like to talk about. I want to begin with an overview of galaxy evolution. I know that many folks work in other subfields, but I'm mostly going to focus on extragalactic observations and a little bit of simulation data. And in particular, galaxies are great because they have these beautiful appearances. And every pixel matters. Every pixel that gets to record an image of a part of a galaxy matters. And exploiting that information is going to require us to use some sort of vision-based method. And I'm going to talk about convolutional neural networks, which is going to be the tools of the trade to exploit that morphological information of galaxies. Third, I want to talk about a way that we can use GNNs as tools. And so this is really almost treating it as a black box method to find new dwarf galaxies and satellite galaxies, which can then help us probe the nearby universe. And finally, talk about sort of the effects of large-scale environment, or location, just thinking about how the galaxy, how they reside in their dark matter halos is impacted by their large-scale environments. I don't need to use the arrow keys here, so let's get started with this overview here. So we know in the lambda cold dark matter paradigm that there's hierarchical structure formation at early times, and so in these large cosmological simulations, even if it's just n-body simulations, only gravity, we know that at early times you have mass kind of gravitationally collapsing into these virialized, or basically self-gravitating bodies, which we call halos, these dark matter halos. It's centered on a very massive halo that began forming at high redshift at early times. But also we can see that there are these other smaller halos, these sub-halos, which orbit around this central halo. And so this is all happening just in the dark matter side of things, and that sets kind of the backbone of structure. But if we turn on our baryonic vision, for example, in this simulation, a different simulation, we can see things like the gas, right? The dissipational forces as gas also, in normal matter, or baryons as we like to call them in astronomy, stream into the sites where, in the innermost regions of this image here, right? This is something like, many megaparsecs across. This is only something like of order, 100 kiloparsecs across. And you can see that gas is streaming in, cooling, and condensing into clouds. And as those clouds continue to self-gravitate and actually undergo runaway collapse, they form stars. And so this is really what we're talking about when galaxies are forming and evolving, is the formation of stars. They're assembling mass and they're turning it into stars and shining. Okay, I like to think a little abstractly at times, and so in the statistical sense, galaxies can be represented according to this curve. You've got this star formation history at early times in the universe, and when it first forms. maybe it is able to accrete a bunch of cold gas, and therefore the star formation rate ramps up over time, so it's building up mass. And then there's a cosmic noon. We think this happened around redshift 2 or so. And then, overall, the big picture of the cosmos is that it seems like, many galaxies after that seems to form less and less stars. And then perhaps you observe this at some low redshift. And at point of observation, you've got, the star formation rate there. But this whole curve, this blue curve, is the star formation history. Now, that curve is physically tied to the chemical enrichment history, which I'm representing in this red curve. And this is the rate of production of heavier elements over time. This chemical enrichment history follows, it lags behind the blue curve in time, and that's because those heavy elements have to be nucleosynthesized in the interiors of those stars. They also have to somehow get out of those stars, and this is, of course, is a whole range of study there, understanding the chemical evolution in galaxies. So physically, we know that these two things should follow each other. As I mentioned earlier, I'm an observer, which means that I like to think not in terms of things evolving over cosmic time, which we cannot observe. Rather, we can see things like the star formation rate instantaneously at the end point of this time, at the point of observation. So maybe that's a SFR here. We can look at the stellar mass, which is, to very rough approximation, something like the area under the curve of this blue curve. Because this is just all the stars that have ever formed. Of course, there's more to the picture, but to the first order, we can go with this very simple relation. And then this Z gas here is you can think of this as a gas phase metallicity, which is the amount of heavy elements, or really the abundance of heavy elements that has formed, and been put out into the gas phase relative to the primordial hydrogen. And that's kind of like the area under this red curve. Again, very simple.
It's dot gas.
I'm sorry?
If the cumulative, how can it go down? No, I see.
Oh, it's the integral under that curve.
Z is the integral.
Yes, Z is the integral. That's right. Yeah. So phi is just this chemical enrichment function. This is a very simple toy model, and it's not meant to be interrogated in detail. I think what I want to give here is more of a physical intuition about the fact that these two quantities, these are the integrals of these two curves, and I just said that one of them lags behind the other. They're physically connected. So when we think about these two ways of describing galaxy evolution, it's stellar mass and its gas phase metallicity, you would expect that these two should be correlated. And indeed, if you were to get the masses and the metallicities of about 100,000 galaxies, as the Sloan Digital Sky Survey did about 20 years ago, you find this tight scaling relation, the mass metallicity relation, MZR. And my point, again, is not that this is a great model, but rather that we have a very simple physical intuition for why galaxies assemble stars and how that leads to chemical enrichment and why we end up with this nice scaling relation. And of course, this is just the first step, right? People have made far better models. You should be thinking of better ways to track different phases of gas in galaxies, think about how cooling functions work and et cetera, and dust formation. But those are all nice and better. These advanced models can do far better in terms of making predictions about how the mass and metallicity ought to behave. But we haven't considered one extremely important thing about galaxies, which is their beautiful appearances. I got into galaxy evolution because I was like, wow, these things look gorgeous. And here we are talking about just little dots or little curves like this, which are not that beautiful. And in fact, right, we know that since the time of the Hubble tuning fork, we know that galaxies come in all these shapes and sizes, and that their appearances really tell you the story of how they formed and how they've evolved. So the morphology, in other words, it's connected to and it reveals the physics and the evolution of the galaxy. To drive this point home, and we often do work with these photometric catalogs. We take 1 billion galaxies in a large survey, and then we say, well, I don't have the storage to deal with all these images. Let me just summarize some of their properties in maybe some photometric colors. And so this is an extremely boring 2-column table of galaxies. They all have the same R-band magnitude and color. I did that on purpose, right? There's just no diversity there. But in reality, they tell you a whole range of different stories. These are the same 9 galaxies, and when you look at their images, you can see a lot more about how they formed over time, something about their assembly history and where they're headed as well. There's just so much more information in that image domain. And finally, we have the tools to process that at scale. So I'm going to start talking about convolutional neural networks, which will be the tool of the trade to get this job done. So I'm actually going to give a bit of a summer school lecture tomorrow on this in more detail. In fact, we're going to go through a Jupyter notebook, but I want to give a high-level summary of how these convolutional neural networks operate. So you can think of artificial neural networks as being able to process some sort of input data. So in this case, here's an image cutout of a galaxy from the DESI legacy imaging surveys. It is just a very complicated nonlinear function with many, many fitting parameters that makes some sort of prediction. So let's say we want to predict the gas phase metallicity, something that's ordinarily accessible just through spectroscopy. You can't typically get it through photometry, or at least we didn't think you could do so very accurately. Okay, so we want to use something called a convolutional neural network, which is composed of convolutional layers. And if there's one intuition to think about for convolutional layers, you should just think of them as feature finders, right? If you've done matched filtering, it's just that. You've got an input image, which is your x's, your inputs, into the convolutional neural network. And you're interested in a particular morphological feature, basically a shape, as represented as in this pixel grid as just the shape, the intensities of the pixels of that shape, right? So if this was a matched filtering algorithm, this could be some sort of filter. It could be a Gaussian of a certain width or et cetera. But in this case, it's an arbitrary matrix. And I've drawn it as a 3x3 matrix. And you take the convolution, which is just to say, you want to see how similar the input image is to that morphological feature. And that similarity, if it's high, then it tells you that your image resembles the filter at that particular location. And you can slide this kernel or this filter over your input image and thus build up a map of how similar your filter is to the underlying image at each location. This is the essence of a convolutional neural network. Now, one extra thing is I've shown that there's this little function f here, and this is a nonlinear function. A convolution itself is a linear operation, and so you have to add this nonlinearity in order to learn arbitrarily complex fitting functions. But once we have this is a very powerful technique because you go from some sort of image to a map of features. In other words, another higher level image, something with semantic meaning. And in fact, you can even take that next layer, the outputs, the activations, and send that into another convolutional layer and build up more abstract representations of interesting semantic features and morphological features on top of that. And so this is what CNNs do. You progress from the image, which becomes, turns into a map of some sort of features. Let's say things like simple wavelets or Gabor filters, which are basically just like small PSFs. But then beyond that, you can come up with more abstract representations, maybe things like spirals or curves in general, or things like dust lanes and H2 regions and other types of things that you expect to find inside a galaxy. I haven't really told you how we get these filters yet, but at the end of the day, you would hope that you build up a list of features, essentially all the possible semantic content that's present in the image, and then that could be something like, you can think of this as a row or in a table which contains a whole bunch of morphological features. So I'm representing this kind of bar chart here as a whole bunch of strengths of various features. Maybe one feature is something like how point source-like the object is, how asymmetric it is, whether it has tight winding spiral arms or so on. This is again, a simplified version of what really goes on. And in fact, it's actually totally wrong. I'm going to say a little bit more about this in a moment. But you can work with this toy conception of it and say that this set of features can then be linearly or possibly even non-linearly combined in order to make that kind of prediction. And so this is kind of the classical way of thinking about that. Now, of course, in the beginning, when you train this neural network, it's actually randomly initialized. It's just a whole bunch of, a million totally random parameters, and it will give you a totally random answer here. And what you do is you say, I've already observed this galaxy. I know the true spectroscopic metallicity. I've observed it and I fit it with some physical assumptions and so on. And I've derived the true metallicity of that galaxy, just this one in particular. And in this supervised machine learning case, we can then compute how incorrect we are, the loss function or the error. So you might say this was a totally random prediction. It was very wrong, but we know what the truth should have been. And then when you can do that, you can then compute the gradient of that loss function with respect to every single input parameter. This is just taking a derivative and then lots and lots and lots of partial derivatives using the chain rule to every single of the million or 10 million or even billion parameters in the neural network. And this is basically how all modern machine learning is done with neural networks. It is just the simple definition of an error, some sort of prediction versus the true value, and then lots and lots of chain rule backpropagation. Of course, that's where all the complexity arises, and people want to do this in more efficient ways. I'm not going to talk about that. But what we can see, though, is that maybe we nudge all of these weights in a way such that they make better predictions. You then can iterate with this and make even better predictions down here, and then your error will go down. You will do better over time, and your neural network will be trained. OK, yep, question?
A lot of the things we do with machine learning tend to be very much at the input and the output.
Mm-hmm.
Is there any way to recover the information between what the feature and the model, or
yes.
what criterion the machine used to classify the galaxy? Because that would be relevant also to try to see.
Yep, indeed, yeah. I think that's a brilliant point. I'm going to weigh in a little bit on that in a moment. So this all falls under the guise of AI interpretability, which is relevant for people who care about AI safety as well, because they also want to know what their large language models are doing under the hood. And so there are a range of techniques. One of the subfields in that is called mechanistic interpretability. So I do some research in that as well. And I'm going to talk a little bit about that, but not a lot. But I'm happy to chat more later. But what I do want to arrive at is that these CNNs are just very powerful. This works extremely well in the limit of large data. In fact, this is kind of what opened my eyes to the idea that machine learning really can be powerful in astronomy. So we can train a CNN just to directly go and predict the gas phase metallicities. If you have good eyesight, maybe you can see even the values of the predicted and the true values of these metallicities. But they conform to our expectations that the metal poor objects are these kind of dwarfy looking objects. These metal rich galaxies tend to be much more evolved galaxies. And if you just look at random samples, we end up being able to predict the gas phase metallicity to about 0.08 dex in 12 plus log O over H. Okay. This is good enough to completely reconstruct the mass metallicity relation here without spectroscopy at all. So we can do this purely using photometry, right? And this is on a held out training set and everything. What we find kind of miraculously is that the red lines here show you the CNN predictions, the neural network's predictions over a range, about 3 orders of magnitude in stellar mass, and it tends to do, it adds no extra scatter to the mass metallicity relation compared to the scatter that already was present when you use the ground truths, the spectroscopy. And this is from Christy Tremonti et al.'s seminal work. So what we think is happening is actually that this scaling law in the mass metallicity relation in black here, we actually know that there are ways to lower the scatter, to tighten the scatter. Some of that variance is explained by other physical characteristics. And in fact, the fundamental metallicity relation, if you've heard of that, is one such example where we think the star formation rate, or maybe the cold mass, actually a cold gas mass, is something that lowers. If you control for that variable, then you actually can predict the metallicity to even tighter scatter. And what we think is happening is that the CNN is leveraging morphology as a variable, even though it's not just one variable, as a way to tighten the mass metallicity relation scatter, so that ultimately when you reconstruct this, you are not adding anything extra. In other words, we think that machine learning is really telling us something about the physics of the scaling relations of how these galaxies grow over cosmic time. I spent a lot of my PhD actually working in radio astronomy. I spent a lot of time in South Africa actually helping commission Meerkat and working on the source finding pipeline there. So H1, the 21 centimeter emission by neutral hydrogen, is very near and dear to my heart. But one of the interesting things that we found in this paper that I wrote 6 years ago is that we can predict the H1 gas mass very accurately. But even more interestingly, we can actually do counterfactuals with these neural networks. So I've trained a CNN on the basis of these images to predict whether they're gas poor or gas rich. I'm just kind of simplifying things right now. And in this case, this is a very gas rich galaxy. And we can look at the pixels that it examined. This is a bit getting at your question. You can see where it's looking at. There's a heat map of where it's inspecting in order to make its classification that this is actually a very gas-rich galaxy. And you can even look at the certainty that it claims to have. But you can do a counterfactual and say, well, where would you have looked if you thought that this was a gas-poor galaxy? And indeed, it looks at the sort of redder stellar populations in the center of that galaxy. So it's looking at the bold star populations, which does conform to our intuitions. This helps give us a little bit more confidence that it is looking at the same types of things that we would look like, we trained astronomers in galaxy evolution might be looking at if we were to evaluate if this is a gas-rich or gas-poor galaxy. Interestingly enough, we can also do, for instance, take away the color information and think, where would it look like? Is there something about the structure formation? Is it doing a bulge disk decomposition somewhere in here? And looking at, whether the surface profile on that outskirt is exponential or whatnot. We can speculate about these things, but ultimately my point here is that there's a lot of rich information we can get from convolutional neural networks. And this is the really crazy part that made me go all in on machine learning for studying galaxies. We were able to predict the entire STSS-like optical spectrum just directly from imaging. So this is from Pan-STARRS imaging, GRIZY. In this case, we have the spectra with the observed spectra are shown in black. You cannot see them because they're almost completely, perfectly overlaid by the predictions, which are in red. They agree to that, good accuracy. And what we've done is we've de-redshifted, the galaxy spectra, and we've interpolated them so they all land on the same grid. And we've done some kind of simplifying things, right? So I don't think that this is exactly, the same thing as saying it's, super resolving and putting the spectrum in the right place. But what this is showing is that the mapping from galaxy images to their optical rest frame spectra is actually really, really tight. That relation is, we know it's dictated by the physics of how galaxies form and evolve over time. But somehow, the mapping onto the spectra is present. And you might be thinking this is too good to be true. That's definitely what I was thinking, that we had done something wrong. And so, okay, we're gonna skip that slide, I guess. Anyway, oh, this is actually what I wanted. Yeah, so what happened then is we found this galaxy. This is the innermost region of the galaxy, sometimes known as Rubin's galaxy. And we found that this was a galaxy that was outside of the STSS footprint. So there was no STSS-like fiber placed at the center of it. But one of my collaborators said, John, hey, I heard you have this cool new method to predict the spectrum of a galaxy. Can you go and predict the spectrum of this object for me, UGC 2885? I was like, sure, why not? Let's just see what happens. And we were able to predict the spectrum, fine, but was it real or not? We then went and took actual spectra with 3 different telescopes and actually dug out some really old spectrum. We had a sort of from a photographic plate that was taken in the 80s. And we basically combined a whole bunch of these spectra together, extracted their emission line ratios, and made this BPT diagram, which is a good way of tracing the excitation and ionization conditions in galaxies. And what we found, and typically this BPT diagram, shows line ratios which can separate AGN, active galactic nuclei, from star-forming galaxies. And so these are just where typical galaxies might land in the black. And what we found for this object is that our CNN prediction, shown in blue here, predicts, analogous to an STSS fiber of 3 arc seconds, that this is what the line ratio ought to be. We then took, a 1 arc second fiber, so this is some IFU data and some other data, which is much more centered on the nucleus of the galaxy. And it shows, indeed, that this is a galaxy with an AGN, but not only that, it is one that is not as diluted with the nearby stellar populations, and therefore it has even higher O3 over H beta. And then from the MMT, we actually had more new data taken where we had 4 arc second apertures, which is indeed more diluted by the surrounding star-forming ring around the galaxies in the center there and the bulge populations, and that gives us something that is also AGN but sort of washed out. And so what we actually know is that this CNN, this neural network, is learning not just to predict the emission line in the spectrum, but the aperture effects of it. That's how much it knows about the data set. And this is both good and bad. It just shows that our CNN works, but we can also physically explain why it is actually giving us a value that's somewhere in the middle. So again, this is like a totally independent held out test. We were amazed that this worked at all. And indeed, this is a paper you can find in Benahuerta's work.
What happens to your old one in MMT?
That's a good question. I think it just doesn't touch that. Maybe in the wavelength coverage doesn't cover it or something. I can't remember exactly, but if you read the paper, we'll probably explain it.
The green squares are actual measurements?
That's right. So these are expected. We extracted all the spectral lines and we got the spectral line measurements. So the green and the red are real data. The blue is predicted by a neural network. And they are consistent and also follow the trends we would expect from aperture effects.
You instantly do this blue for both 1 arcsecond and 4 arcsecond and see where that goes?
Yeah, so let me think. So, I mean, these are a variety of things, right? This is an IFU, so I think we could make something like a pseudo 3 arcsecond aperture for that.
I thought for a CNN, it's just 10 seconds. You tell it to do it for 1 and 4 and you're done.
Oh no, but the CNN has never seen, has not been trained on 1 arcsecond apertures. And so it doesn't know what the spectrum of a 1 arcsecond integration of the spectrum looks like.
But going to 4 should be instant. No, you're saying it's not.
No, in fact, it knows the systematic effects. In fact, it only knows the systematic effects there. So the CNN, so this is a limitation of neural networks. They really know their training data set well, but they do not generalize beyond anything they haven't seen.
So you're saying that some spectrum fibers are 3 arcsecond in
Yep.
diameter. So given that the spectrum contains the redshift, the model knows how large an area it covers in a galaxy.
That is true, yes. It also learns things like the apparent sizes and the apparent, yes. So it learns all these different things. I've actually explored these in a few of the papers as well. So we discussed these kinds of things. Now, so yes, it knows the apertures. It effectively has to learn something about like an approximate photometric redshift, and it learns something about the aperture corrections as well. But it cannot actually disentangle all those things. Now, if I took this model and then I trained on all the DESI spectra, which span 1.5 arcsecond apertures, it will probably give me, a nice little measurement up there. So this is, it's hypothetical, but we could do it. Yeah.
How representative this galaxy would be of the typical galaxy in the training set?
That's a great question.
That's the other point.
Indeed.
Your machine learning cannot be any better than the data you trained it on.
That's correct. Yeah, and so we thought that this was actually going to fail for a few reasons. One, it's relatively nearby, although I've zoomed in here just to show the aperture corrections, but it is within the convex hull of input data, so it's not completely bizarre there. But it was a strange galaxy because this is one of these almost like super spiral galaxies, so very, very massive, something like 10 to the 11.2 or so in solar mass and log stellar mass units. So very much at the top of all scaling relations, and we actually weren't sure if this would adhere to known scaling relations. Now since then, actually there have been other papers, in 2023 or so by Patrick Ogle and others that look at these super spirals and find that indeed they do fall on the known scaling relations in terms of velocity and and luminosity size and all those kinds of things. So this is another almost sort of unintentional confirmation that this, at least with whatever scaling relation the CNN is learning here, something between the morphology and its BPT sort of classification, that it also adheres to that. So that is a good point. But it does pass the test. All right, I think I'm going to keep going here. I just want to highlight a work one of my students is doing, which actually does this entire thing that I've been talking about, but in a statistical sense. And so you might be familiar with spectral energy distribution fitting with SEDs, which are again extracted over some known aperture. But indeed, we can now break SED fitting degeneracies by using their images. So if you take the images and you look at some physical properties which are fit by SED-like methods, what we're doing here is actually a neural posterior estimation type technique. So it's really like training on the outputs of some sort of physical modeling and then using a neural network to amortize that and doing it in a full probabilistic sense. We can find that the blue posteriors generally adhere better to the spectroscopic, basically ground truth version of it, compared to just the SED only, where you're sort of not aware of the morphology. So again, this is work, we have a sort of a machine learning paper that has already been put out, and that's on arXiv, but we've got sort of a longer AppJ paper. It's about to be submitted. Okay, oh yeah.
Sorry, these are real galaxies.
These are real galaxies, yeah.
So how do you know the ground truth?
Good point, yes. So the ground truth, of course, is conditioned or dependent on lots of physical modeling assumptions. So this includes, simple stellar populations and a grid of possible, fitting outputs and things like that. So we do have to rely on other assumptions, right? It's the truth. That's why it's got these quotes here, right? They're as true as, the assumptions we put in. But they use spectroscopy to sort of derive stronger constraints. So whatever types of degeneracies that can be broken by having spectroscopy, right? Knowing DN 4000, knowing emission line ratios, and knowing other types of things, like breaking the dust age and metallicity degeneracies and things like that, if spectroscopy can help us break those degeneracies, it turns out that imaging also lends a hand in the same direction. That's basically what we found. Yeah.
Sorry. But previously, you already said that from the imaging itself, you can already predict the spectrum.
Yeah, yeah.
So what's the value of
Well, so these are consistent. Yes, exactly. You're right. These are consistent, but mostly when people talk about I want to do SED fitting and derive the properties of a galaxy, you throw away the image, right? And what I'm saying here is that you actually, and in fact, SED fitting is important because you want to have uncertainties, right? You need to have a full posterior, and you want to understand the covariance between your modeled parameters. We can still do that with images now. So this is now not using, this isn't just predict a spectrum, who knows how uncertain it is, but this gives you full uncertainties. We can calibrate and check, whether or not with posterior predictive checks and all sorts of, accuracy plots and things like that to evaluate the calibration. And indeed, we find that this does a pretty good job. But really the important part is that this gives you a full posterior, and you can now combine this with other constraints, like maybe you have some far infrared or some radio constraints or some X-ray constraints that give you another handle on some sort of modeling. Well, you can do that here, whereas if you were just to predict the spectrum, then you don't know the statistical way to combine that information. All right. All right, I'm gonna hurry through here. Okay, sorry, I did want to talk a little bit about the interpretability, but all I can really say is I think I want to kind of move through this more quickly. You can actually induce interpretable features by forcing the neural network's activations, the internal mechanism, to be sparse, and that way it consolidates, similar types of features. And what we find basically, without really trying to produce coherent galaxy populations and things like that, that various activations within the neural network, if you look at what they activate, they give you very coherent properties. So this is an example where essentially I'm just looking at 4 very frequently activated features. This is like a neuron in the neural network. We see when does this thing fire, and what we find is that for low mass sort of dwarf galaxies, which are also low metallicity, and you can see that these are activating sort of in the corner of this BPT diagram again. This is where you expect dwarf galaxies with relatively low metallicities to sit, and indeed that they look like they should belong to that class. Here you have galaxies that are maybe more like liners. They have older stellar populations and perhaps AGN in them, and that's where they sit in this region of parameter space. But indeed, morphologically, we can actually pre-select on them and get a very clean sampling. Again, very consistent with what we saw before, but in this case, we are not actually training it to come up with a self-consistent or a coherent set of features. We're just saying, you need to have sparse features, so consolidate this in a way that's efficient. And indeed, that sparsity creates very interesting things where we can now go and study. One of the things I'm most excited about is this particular neuron in this neural network. This seems to find extremely high ionization objects. So you can see that their activations, if you have good vision, is sort of highlighting very close to that boundary there. And this tends to show up when you have very strong ionization, extreme emission line galaxies. And indeed, their appearances look like that. I spent some time working on Lyman break galaxy analogs. They look very much like Lyman break galaxy analogs or other ELGs. And in fact, a lot of these actually, if you look at their spectra, have nebular excess, and they have very interesting ionization conditions. They excite the neon 5 and neon 3 lines and so on. So these are all very interesting objects, and we've pre-selected this sort of by accident. Like that wasn't the goal to find them. It just turned out that the neural network allocated a neuron, said these things all look the same. They're kind of interesting, and so there they are. Here's some low surface brightness objects. They seem to have relatively low pressures in their disk and so on. And so they all sort of have physical explanations, but the story is all the same, which is that if we want to use neural networks to understand physics, we actually can start to tease them apart and explain what it is that they're looking at and try to understand like the modes in which they are defining scaling relations and things of the physical processes that we know.
The color does not mean anything.
No, sorry, the colors just are, these are arbitrary. They're kind of, I chose them because they almost look like the colors of the galaxies. But they're not meaningful. The intensity, so the brighter colors are the ones where the highest activations are. And so you can see that these are close to the dividing line. Okay, so that's it on CNNs and interpretability. Now I want to talk about using these as black box methods. Why would you do that? Well, sometimes even if there's a method that is not totally understandable or whatever, you can still calibrate how well it performs, and you can understand whether it might be useful to you. You can understand its biases and all those sorts of things and carefully measure those. So I'm going to talk now about a valuable application of machine learning to find dwarf galaxies. So first I'm going to issue a challenge. Hopefully the projector screen is good enough for this, but this is a Milky Way-like galaxy. It's about the same mass of the galaxy, of our Milky Way. And I'm curious if you can go and find all the satellite galaxies that are orbiting around the system, at least shown here. And I want to talk about satellite galaxies, which do reside within the dark matter halo of an L-star or a Milky Way-like galaxy, like this one here. And they're really interesting because they live a tough life. They get easily destroyed or disrupted by all kinds of physical processes. So for instance, at early stages, cosmic reionization might zap away all the gas in them, and they never form any stars because they're just a hot halo, and so you just got this dead halo, subhalo. They can have star formation feedback, which might cause them to blow themselves apart. So one wave of old stars form or massive stars form, and then that's kind of it. They never form stars again because they've heated up all their gas. They can feel the ram pressure as they fall into the hot halo of a massive galaxy like this, and that can strip away all of their star-forming gas, and so they have no fuel to form new stars. Or perhaps tidal forces will shear them apart, right, and disrupt them as their orbits decay around this galaxy. So they are very sensitive to all kinds of physics, and therefore they are also great for all kinds of comparisons to theory, right? The assumptions that we put in, things like lambda CDM or the nature of dark matter, whether it might be warmer or self-interacting, that can change the number of satellite galaxies you might expect to find. Same thing with galaxy formation physics, right? If you think that there's a star formation efficiency of some amount, or you blow out gas with some particular efficiency, you couple the feedback back to the gas in some sort of way, depending on AGN versus star formation. All those kinds of factors that you put into your simulations are going to change the mapping between how many n-body subhalos you have in a simulation to how many observed dwarf galaxies are in your Milky Way or local group. And indeed, if you've heard of like the missing satellites problem or the too big to fail problems or these kinds of issues, there are discrepancies, or there have been discrepancies between observations and simulations. Now we think that a lot of baryonic physics can actually address these kinds of these issues, like the fact that we predict that there's something like thousands of dark matter subhalos orbiting around a Milky Way-like system, but maybe when we observe, there's only a couple of dozen of them. And so the Milky Way is one way to look at this. Milky Way and even M31, our neighbor, are very well-studied systems. So that's one way that we can get a sense of like how well can we simulate or put in these physical prescriptions into our simulations in order to match our observations. But we also need cosmological context, because this is, the Milky Way and M31 might be odd. I mean, they're just two L-star galaxies. They're near each other, but it's the best studied one. We need more of a statistical inventory. Okay, I'm just going to return to this now. So I hope people were able to see these two satellite galaxies that are pretty close by to this Edge-on massive disk galaxy. Indeed, these are very low mass. These things are pretty fuzzy. In fact, they're too faint to even be confirmed by DESI because they're something like 22nd magnitude. So in the main survey, they would not be found, or they would not even be targeted. If you have extraordinarily good eyesight, or up the contrast dramatically, you will actually also notice that there's a very interesting little smudge up there, which could be an ultra-faint galaxy. And I remember staring at this thing for a long, long time. And then later on, the Dragonfly survey also noticed, that's what's being shown here, there's the GNR imaging, that there's the smudge next to this massive L-star galaxy. And they think it's actually Cirrus, galactic Cirrus, just masquerading as maybe an ultra-faint dwarf. But it's quite hard to basically finding these satellites. Like, this is a really hard challenge. I'm proud to say, though, that the satellites around galactic analogs, so SAGA, is a really comprehensive survey. In fact, it's now completed. And this collaboration has taken a spectrum of like every potential dwarf galaxy around a Milky Way-like system at about 25 to 40 megaparsecs away from us. So what they do is they look at the projected virial radius around a massive galaxy, a Milky Way analog, and then take a spectrum of every single thing that could plausibly be a dwarf galaxy candidate. And this is extremely, extremely rigorous, right? Observationally, this is talking about like getting of order 75,000 new spectra. As you can see, they were able to confirm 378 satellite galaxies. So we're talking about a 0.5% efficiency observational campaign. And the fact that they were able to somehow get this into time allocation committees and to observing proposals is just miraculous, right? If you say, oh, 99.5% of your spectroscopic fibers are going to give you something I don't care about, I can't believe they would do this, but this is really just a fantastic data set now. You've got 101 host galaxies where only a fraction of a percent were able to be confirmed, but it is very, very complete now in terms of capturing a census of these dwarf galaxies. You can see all in the background here. Okay, so that's beautiful, and I should say we were able to do a lot of great science there. But in fact, we can also use this valuable data set. One person's trash is another person's treasure. And in my case, I was like, hey, there's tons and tons of failed spectra, or basically higher redshift objects, which are not satellites around these very low redshift galaxies. But we can do something with them. We can train a CNN to distinguish between the very low Z galaxies and the very high Z galaxies, or the higher Z galaxies. Now, this is arbitrary. There is no such thing as a class which is low Z or high Z, right? This is just something I invented. But it's something that can be a useful tool if you really are trying to find objects that are like those which would turn out to be low redshift dwarf galaxies and perhaps satellite galaxies of Milky Way-like systems. And in fact, we can train on the entire SAGA sample and then go out across 20,000 square degrees of field in the legacy DESI imaging surveys, the DESI legacy survey, and look at all about, I think, 6 million galaxy image cutouts, which is what we did, and made classifications across this entire wide field sky. So then we can say, well, we can find objects that look like they might be low Z and objects that don't look like they're low Z, but who's to say what's the ground truth here? Well, what we did then is we went back to DESI and we said, you have a bunch of spare targets, actually. They're not able to allocate all of their 5,000 little fibers. And so we got a spare targets program where we then tried to say, let's evaluate the CNN selection technique. Are these really low redshift galaxies? Or in other words, we know that SAGA's trying to find as many low redshift objects as possible. And in fact, they have these really well-tuned photometric selection techniques on the basis of colors and surface brightness and so on. And those are actually shown in the purple and the pink here. Those give you distributions of redshifts that, and we're looking at objects that are less than redshift 0.03, are, again, like a fraction of a percent able to capture these very, very low objects. Most of them are at more intermediate or higher redshifts. But what we did with our CNN, and in fact got real DESI time, in fact, the DESI survey is now complete, so we have the largest catalog of very low redshift, very low mass objects ever compiled. Viraj Manwakar at Stanford is compiling that, but Elise Tarak-Ford also at Stanford worked with me to go and make this happen. And so this was based on early data release DESI data and year one results. So you can look at this at the early stuff, and what we found indeed, if you just, you can see from the histogram that we're getting something like an order of magnitude higher precision or basically purity, right, in terms of being able to select these very low redshift objects with the CNN. So again, order of magnitude increase in observational efficiency. This is what machine learning can let you do. Okay, what else can we do? Well, it's great and all that we can go and launch this observational campaign, but they're not actually going to get every single object out there. I mean, there's a finite time to the survey. In fact, it's done. We're thinking about DESI 2. But there are lots and lots of targets on Sky that we would love to get additional spectra of. So here's all with Sloan Digital Sky Survey. This is the NASA Sloan Atlas. All the objects as a function of our magnitude in some piece of sky that we've already known about. So this is a good number. What we were able to do using this trained convolutional neural network is fill the sky with lots and lots new candidates. Okay, so I'm calling this XSAGA because we are extending the SAGA survey with machine learning. And so what XSAGA is doing is saying, there are lots of possible low Z galaxies, in fact, over 100,000 of them found with the CNN. And as I just showed, we empirically validated tons and tons of them. So in fact, many of these now do have spectroscopic confirmations. But also, importantly, many of them were wrong. they were wrong, they could be false positives, and there could be other things that we missed that other surveys found, so we are incomplete as well. We can be wrong in many different ways. Importantly, we can calibrate how wrong we are. And we can calibrate that as a function of surface brightness, of magnitude, of color, all those sorts of things. And so in a series of these papers, we were we have these extremely long appendices about exactly how wrong we were and why we think things went wrong and what the CNN is doing in terms of biases. But we can measure those things. And when we can measure them, we can now correct them and do interesting statistics with them. And so what we can do with these objects, again, these very potential candidate low-Z galaxies, is say, well, if they are very close to, like within the projected virial radius of a known massive galaxy, well, we know that galaxies cluster, and we know that substructure exists, and so therefore they are much more highly probable to be satellite galaxies around a known satellite, around a known massive system. And indeed, you can actually look at some of these, right? So here's an example. This is like a Milky Way-like analog at redshift 0.029. And here are 5 objects that ExSAGA found. None of them have spectra, including even this one. They're just, I guess they were never targeted for any reason, but they all look like, they look like satellite dwarf galaxies. And in fact, we know that probably, one of these 5 is wrong, and we know that we might have missed another one out of the 5. So again, I'm saying we can do the statistical analysis of how many satellites there are around it. Here's another system, where we actually see that this has a confirmed, spectroscopically confirmed, which is why it's got this yellow box around it. This is kind of like a LMC analog around a Milky Way-like object, but we found 2 other objects in this system. So this is really great because we can start going to a different, redshift, a slightly different redshift regime than the SAGA's very stringent selection. We can also go into environments like group environments where there are a whole bunch of known galaxies, but also a whole bunch of very faint objects where we are able to find and probabilistically label as these could be satellites, but we're not sure. Let's see what happens, right? And so this is the kind of science that we can now do. Specifically, what we can do, I'm going to give 5 quick hit results. 1, we can find that satellite abundances vary dramatically with host mass. So this, what I'm showing here, is the number of satellites in different stellar mass bins of the host. So as a function of the stellar mass of the host galaxy, how many satellites are there within some projected radius? This is using all the correction factors I talked about earlier, and we can measure these basically within 300 projected kiloparsecs, and we find indeed that there's a very nice statistical trend with host stellar mass.
You implicitly said that you've got a 20% error rate and that you know it's 20%. How do you know it's 20%?
Because we have lots and lots of spectra here. We have...
From this comparison.
Yeah, we have 5 years of DESI spectra so we can calibrate them, and so indeed, yes. If you look at this paper, there's a lot of discussion about how incorrect we are, what the false positive rates are. There's a lot of other thresholds and things in this CNN that I haven't discussed, but there's a lot of discussion surrounding that as well.
That 20% is related to 19%, or that's an unrelated number?
So it's partially related. This CNN is using a slightly different threshold. It's the same trained CNN, but we basically are willing to be, in this case, we want to be emphasize completeness over purity. So we have a higher false positive rate here. We have more like an 80% false positive rate. This distribution is more stretched over to the right, but in the ExSAGA version of this, it is tapering off much more. So that emphasizes, it balances the false positive rate against the incompleteness. I think maybe the details of this, I'd be happy to chat more later, but yeah, there's definitely a lot of details in here, and I don't have time to explain it. But what I do think is important is that the results also sort of, one, they're more statistically significant than anything we've ever done before. We in this case have basically increased the number of effective satellite systems that we can study by 2 orders of magnitude. And so for the first time ever, we can differentiate the number of satellites as a function of stellar mass of the host galaxy, while also finding that there's basically no variation in the radial profile shapes, which is kind of an interesting finding. But we actually tested how the radial profile is normalized. This is work that I did with the SAGA team, and indeed we find that there's not a whole lot of variation here. This is super interesting to Yaoyuan Mao, actually, who I think is an alumni of here. We worked very closely together on this particular paper. Another interesting thing is we find that satellites probe the dark matter halo accretion history. So the satellite abundance, as I've just shown in the previous slide, can be compared against the magnitude gap. This is essentially a proxy of how recently the halo has had infall of satellites. And that there's kind of group infall of satellite galaxies. So there's a lot of interesting physics in here. But what we can actually do is measure this all as a function of stellar mass of the host galaxy. So this tells you something about the host galaxy's disruption efficiency as a function of their stellar mass. And that's telling a story of that by their slopes here. Yeah.
Maybe I'm a little bit confused by the number of lower mass objects. Maybe it's a naive expectation, but I would be expecting in terms of the initial mass function, we'll have a lot more lower mass objects and then less and less massive objects around, even if they are satellite galaxy or example. And that's what the plot showing me, if I understand it correctly, is the exact contrary. But a lot of massive objects and less lower mass objects.
Sorry, you're talking about this plot, yeah? Okay, so
Or the other one too, the same.
this one?
Yeah.
So this is as a function of projected radius. So this is a question of, if you look farther out in radius, what is the cumulative number of satellites? And so for the lowest mass host galaxies, you have the fewest satellites around them. And as you go to host masses of something more like the Milky Way or higher, you end up with something like many more objects. And
Okay. It's
yeah.
a function of the mass of the host.
Of the host, yes, that's right. Yes, apologies if not clear, but yeah, this is the host stellar mass, and indeed this as well as showing the host stellar mass in the colors here.
Oh, okay.
Yep.
Thank you.
And indeed this does truncate a particular spot in the stellar mass function for the satellite. So we go down to basically like classical dwarfs, something like 10 to the 7 or 7.5 in stellar mass of the satellite. Okay. A third thing, this is something one of my students at Princeton is working on, and hopefully we will submit in the next month, is we can find different satellite populations as a function of the host specific star formation rate as well. I don't want to get too into it, but we can look at both the satellite abundance as a function of host satellite mass. I did a good job there, right? Actually, I labeled it. And also we can look at the satellite colors as a function of host stellar mass. And we can even fit trends to these and remark on what we think is happening physically. But I'm running low on time, and in fact I want to talk more about more work too about how paired versus isolated Milky Way analogs. Simulations have interestingly found that if you look at a Milky Way versus like a Milky Way plus M31 system, there might not really be much of a difference. But this is usually using a small number of objects in a a small cosmological volume. But we're able to do this with again, like of order, I think 8,000 host galaxy systems. So many thousand paired and unpaired isolated Milky Way analogs. What we find is that there's actually a pretty strong discrepancy between the number of satellites around, paired and isolated Milky Way analogs. And in fact, they have redder populations on average. This is not like wholly unsurprising, but it actually does contradict what simulations have been telling us for a little while. And this is a very, very preliminary work that I've been doing with Hubble fellow Andrew Sagery. But what we find is if you take SphereX 3.3 micron PAH emission, so that gets a very low resolution near infrared to mid infrared spectrum, you can look at the polycyclic aromatic hydrocarbon emission, the 3.3 micron feature. And in fact, what we find is that there, as a function of the host mass, the satellite's stacked emission seems to indicate that there's less dust above a host mass, stellar mass of about 10.2. Again, suggesting maybe something like environmental effects. Very preliminary work though. But this is the kind of thing that we can now do, at unprecedented scale, because we have 2 orders of magnitude higher statistics that we could ever do before. It's all courtesy to machine learning. I see that I have 5 minutes left, which means that I have no way I'm going to talk about this last chapter or bit of this roadmap. All I will say is that let me just say this slide, which is that there are lots of ways that we might be interested in understanding how galaxies, this is now simulated galaxies in hydrodynamic simulations, for example, in illustrious simulations, how they relate to their dark matter halos, right? Under the assumptions that are given by that particular simulation suite. And then there's a question of saying, well, how do we measure the impacts of environment? In order to get there, we actually need to first define the environment. Like, what do we mean by environment? And there are simple ways of defining environment by saying, like, let's just look at the spherical overdensity. You do convolutional top hat filter of some radius, and you say, okay, there's matter on these scales. That's one way to do this, and this is very commonly used. It's very nice and simple. It makes sense. You can do things like topological data analysis using tools like disperse. This is a discrete persistent structure extractor. So this is much more complex. This has nice mathematical theory behind it, and it can maybe carve out something like the cosmic web and the filaments and nodes which are at clusters and voids which have nothing, and so on. Or what I'm going to advocate for is by just empirically modeling the entire cosmic structure with a giant graph neural network. And by graph, I mean mathematical graph, a collection of nodes and edges. They can talk to each other through neural networks and pass messages, which are effectively like, you can almost think of these as passing their physical forces or effective interactions between each other. And in doing so, you can say, given this collection of nodes and the edges that connect them, this is like actually from TNG 50 of Illustris, can we then predict, can we paint on galaxies on these halos? The upshot is, yes, you can do this really well with a graph neural network. A bunch of my students have done some interesting follow-up work connecting this with GNNs with graph neural networks, and we can basically continue to improve performance. In other words, we continue to explain scatter and learn more about cosmic structure, yielding that information to better constrain the stellar mass as a function of the halo mass. So the stellar mass-halo mass relation is generally the way that you quantify these kinds of things, and indeed we can do that. We can basically continue that, but do it much better than with traditional techniques. Okay, and the last thing I'll say is that we basically find that environment at a given redshift or snapshot in a simulation and the full assembly history given by a merger tree as modeled by GNNs essentially give you the same results. They give you the same amount of constraining behavior. And this is really important because effectively when we model simulated galaxies, and if we want to run a giant cosmological n-body simulation and we want to paint the galaxies on, we can do things like abundance matching, which is the traditional approach, and maybe you can even do abundance matching with some sort of environmental proxy. But it turns out that using a graph neural network outperforms that by a lot. It even outperforms these fancy cosmic web topological data analysis models like disperse, and it works just as well as integrating the entire full merger tree over cosmic history. So in other words, we can use a snapshot, right? Like if we have a wide field survey at a given, you take all the structure at a given point in time, you don't have to pretend like you can look back in time. You can actually reconstruct the galaxy halo connection just as well without the merger or assembly history. So that's the upshot there. I'm going to leave my summary here because I'm really low on time. And yeah, thank you all for listening.
So the topology is wavelength dependent.
Yeah.
I'm just wondering, do you have idea about what's the optimal combination of the bands you need to put in as a topology, and what's the best combination of it?
Yeah, I think there's a great point. It's probably, we don't know. Okay, I don't know, I'll say. But you're absolutely right in the sense that if you look at like higher redshift objects, you generally run into a lot of problems. One is K corrections, of course, right? Everything shifts into different observed frames. And the second thing is that the parent size goes down. So the number of resolution elements you have over a galaxy decreases. And so morphological constraints are weaker. Now with with Euclid now online and with Roman about to go up, I think we can start to make better headway there. If you've ever tried to do machine learning on like candles or even like Cosmos Web, with JWST and all these kind of like larger fields, they're still nowhere near the statistical sampling that you need in order to be able to do machine learning at scale. But very soon with Roman and already with Euclid, we've already seen that this is feasible. So I'm not really answering your question. I think that if I were to venture a guess, I would say that I found that optical sort of G minus R, having G and R colors is great. Having rest frame U band is also great because you want to sample the 4,000 angstrom break. Those kinds of things are going to help probably the most. But ultimately, I think it's a function of redshift and all this other complexity there.
So in your example of predicting the spectrum, what's the band you are using? I'm
using Pan-STARRS GRIZY. So it's 5-band imaging, yep. It doesn't have U-band, and interestingly enough, it tries to predict the STScI spectrum, which is a little bit bluer than the Pan-STARRS G-band. And so it actually, that's the one part where that model is basically unable to constrain, what the rest frame U band should look like. And so that's where there are deviations when predicting the spectrum. Yep.
Question about you brush upon very rapidly the where you were looking at the environment, doing you're trying to do like a convolutional neural network, but how do you train the data on what when you want to look at the environment and the cosmic wave?
So so that's using a graph neural network. And what we do is we model, sorry, I had to rush through that a lot. This is probably the simplest way to explain, is that you say every halo in a catalog has a position, and it's got it exists, right? This is a simulated dark matter halo, and you want to do something like predict, the cold gas mass or the stellar mass or its black hole mass or something or other, right? You then build a graph based on its proximity in some way. So you can do this just as in terms of the spatial distribution of these galaxies, and you just say I want all galaxies within like 10 megaparsecs of this galaxy. If it's a neighbor, if it's defined as a neighbor that way, then we can iterate over all neighbors which are indexed by J, for some host galaxy I, and then pass it along to some sort of learnable fitting functions. There's a graph neural network layer. It can then pass messages along the edges. You can also use, in this case, we use E3, basically under Euclidean group action, 3D group action. You can preserve invariance there, or even make it equivariant, and thus encode like geometric symmetry. So there's a lot of fun things that you can do here in a way to make this so that when you sort of re-aggregate all of that information back onto the original object, you can make a more informed decision. You should think of this as saying, I'm collecting information based on, essentially on the distribution of objects around any one galaxy or halo. How do I collapse that information back in a useful way that preserves their structure, right? Their phase-space structure and everything, and then use that to better determine the mass of the galaxy, or stellar mass, yeah.
So I thought Jianhongyu also has a similar software that takes every object in the field and assigns it as being part of an object, part of a bigger galaxy or not. And it has some success rate. So yours at XSaga is 80%. How does that compare to what Jianhongyu does?
It depends on the fraction of galaxies you have spectroscopic redshift to train. So.
But the exact same, that takes the exact same data set that XSaga, that John showed for XSaga. You could just ask Jianhongyu takes the exact same photometric and spectroscopic input, and it also gives you a yes or no for every one of these 100 times fields. Just curious, since it gives the exact same calculable metric, I'd be keen to see, does he get 80%, 50%, 20%?
What is the completeness of this?
Sorry, what is the what?
The completeness, the redshift completeness.
I mean, for XSaga, I'm looking at objects that are less than redshift 0.03, so about 120 to 130 megaparsecs away. As I said, that's a bit of an arbitrary decision, but we find something like 100,000, possible candidates. Now, what we're doing again is we're relying on their image cutouts. So I'm not sure what Jianhongyu is using.
But again, everything which has most of these or many of these certainly do have data points in the photometry, in the photometric catalogs as well. So I'm just curious. This is a totally different algorithm. And you can ask the same question. I mean, there is an answer.
So it has a different purposes, but
No, I know it's a totally different algorithm, but it answers the same question. Are you a member or are you not a member? It's the same answer. So I'd be curious. Maybe just run it. Maybe it's Jianhongyu here. Too bad. Otherwise, we could just go push the button and tomorrow.
We can correspond later, but yeah, I'd be happy to. I think that would be great.
So I don't suppose you just give a point estimator. Your model gives a PDF.
I can, but in this case, no. I do just give a point estimate. Again, it's because with the point estimate, we then the distributions are in the form of like how do we model the completeness and the purity, and in fact there are other sort of contamination fractions as a function of surface density, as a function of volume density, and all these kinds of things. So we consider all these in different ways. And so that's where the maybe there's a more distribution like comes in. Yeah.
all your dwarfs essentially look diffuse like that.
Yeah, many certainly are. So we, indeed, yes, good eye. Not all, but many, yes. So some of them are a little more compact, but in general, I think that there is a bias that we've measured as a function of surface brightness. I mean, it does tend to be a better way to find, like, especially some of these objects. One thing I should say actually is that it's a weird bias. So it is a bias. It's a weird bias because these diffuse red objects are effectively, like, there's no way you can, get the spectroscopically confirmed in a reasonable amount of ground-based, time. They are too diffuse and they're actually quite red, especially for dwarf galaxies. And so being able to try to pick out, like a bunch of absorption features on these things is very, very, very difficult to do. So it's kind of interesting because we were looking for like comparisons on like, oh, how well do we do spectroscopically? And our ground truth sample was horrendously incomplete. There were almost none of these, and we had far, far, far more of these objects. And we realized that indeed, in fact, a lot of these objects are in cluster environments and things as well. So we probably can, we do think that a lot of these are real and probably at that redshift, but our ground truth is actually totally wrong. So, so we have to consider biases in every which direction, right? We're kind of expanding the frontiers of what the samples used to be. In fact, we've improved them by like almost 2 orders of magnitude. So our spectroscopic ground truths are in some sense woefully incomplete themselves. But I'm deflecting in which I'm saying that yes, there are some things that are compact, but in general, they're quite low surface brightness.
How good are you at sort of estimating the redshifts of those things, and the ones that are not associated with an enormous galaxy?
Oh, the ones that might just be in the field?
Does your software have must have an estimate for the...
Not any one that I would believe. Let's put it that way. So we don't we explicitly don't try to do that, which means that indeed things that are out in the field are going to be pretty hard to get a handle on. Like it might be interesting to get a sense of these isolated objects and then like go and follow them up. And in fact, that's what basically we're doing with DESI is to see, oh, which of these are in like totally field environments or even void environments, try to get a sense of their properties. But in general, we rely on this kind of assignment of satellites around known host galaxies with confirmed spectroscopy. Yeah.
And that's what fraction of that?
That gets us something like, so we get something like 20,000 satellite candidates around, whereas we began with about 111,000, 110,000 objects. So less than a fifth are assigned. Yep.
One final question. If not, before we think, let me say again. Tomorrow at 2:30, he will give a tutorial lecture in this room, I think.
Okay.
To some students, but everyone is welcome to join. And yes, he's an expert in AI, so please feel free to ask him for more questions or philosophies on using AI on real life or research. So thank you, John, again.
Thank you for having me.